how much energy does it take to move a +2 microcoulomb test charge from A to B, where A is located over here and B is located over there, and we've got a +5 microcoulomb test charge kind of messing with everything. So the first step of this problem is figuring out what the heck they're talking about, because we've definitely come a long way from blocks going down ramps and stuff. This is some goofy wording going on. But what this is talking about is there's an energy change involved because there's a potential difference between location A and location B. You end up with actually a higher potential here than you do over there. Electrical potential can be thought of sort of as mountains and holes in the ground. Positive charges make mountains and negative charges make holes in the ground, just like you would see for gravitational potential energy. In this case, this is a positive charge, which means it's sort of like there's a big fat mountain here. And if that's the case, then location B is higher up the mountain than location A, which is why there's an energy requirement to get from A to B. And it really doesn't matter what path we take. You could go straight to it, or you could take some loopy thing. Your change in potential energy, the amount it takes to get up the hill, depends on how high you climbed and nothing more. Hopefully you were convinced about that when we talked about just regular potential energy for gravitational. So what we have to do is calculate the potential at both of the locations. We got to find it at location B and at location A. And the difference between those potentials tells you how much energy it takes to move a +1 coulomb test charge from A to B. Because the definition of electric potential is what the potential energy would be for a +1 coulomb test charge. If you don't have that one down, you might want to pause the video and play that again. It's what the potential energy would be for a +1 coulomb test charge. That's what electrical potential means, and you'll do well to memorize that. So I took some pretty big steps here. We're calculating the voltage at location B and location A so that we can just find how much the voltage changes. And the equation to calculate voltage is just KQ over R, where K is 9 times 10 to the 9. It's just a number that you got to know. It's just a constant. Q is the value of the charge that's creating that voltage, and R is how far you are away. Notice how it's not R squared like you would see when you're calculating the force. It's just regular old R when you want potential. So the potential at location B is just K times Q over R for B between these two. And the voltage at location A is the same thing. You just use the different distance because the charge and K are the same for both. If I want to find the the difference in potential between B and A, then I can actually factor out this little section because they both have that in common. And then it really comes down to this, which cleans up the math nicely. But if you wanted to, you could have just calculated both of these one at a time and subtracted them. It wouldn't really bother me. When you subtract them, you end up with a potential difference of 67,500 volts. What this means physically is for every coulomb of charge that you want to move from here to here, you had better have 67,500 joules of energy to do it. Now, in real life, moving a coulomb is a whole lot. You can think of a coulomb kind of like a ton. It would be hard to move a ton from any location A to B. It would take a lot of energy. Plus, a joule is a small amount of energy. So don't let this bother you a whole lot, because the thing that we're actually moving is only a +2 microcoulomb test charge. So let's calculate that out. So now to calculate the actual energy needed, what this is saying is that for every coulomb of charge, you need this much energy to move it. So if you had 1 coulomb, it would take you 67,500. If you had 2 coulombs you wanted to move, then you would need 130 whatever thousand to do it. For every coulomb, you need this much. All we have to do is multiply to find the total amount of energy required, since we're only moving a fraction of a coulomb here. In this case, it would only take a fraction of a joule to actually make that move from A to B for such a small amount of charge. See you on the next one.